So in the world, there are two kinds of charges. There are negative charges, and there are positive charges. And normally when we talk about negative charges, we're talking about electrons. And if we're talking about positive charges, we're talking about protons. That's the normal situation. In this case, they're opposites, so they're actually attracted to each other. So there's a force on each one of them, pulling them together. If, on the other hand, I have two positives, or for that matter, two negatives, they repel. And the strength of this force is defined by Coulomb's law, which is force equals K, a constant, times the charge of one, times the charge of another, all divided by the distance between them squared. So R here is simply the distance between the two charges. And oftentimes we like to take the absolute value of each of the charges, because we're only trying to find what's the magnitude of the force in this situation. And we figure out the direction of the force based on whether the charges are a positive and negative, or two positives, and so forth. Those were forces. Let's take, for example, right now, let's look at electric fields. An electric field is sort of like what a force would be if there were actually two charges. Here I only have one charge. If I put another charge here, there would be a force. So there's like this potential for a charge to actually, for a force to actually exist there if another charge were there. And we call this a field. A field is what the force would be if there were an actual charge there. So if I put a positive charge here, I would get a force in that direction. So if I put, for example, a test charge, and this test charge has a charge of Q, I can say the electric field is then the force on this charge divided by that particular Q. And since the force is just Coulomb's law, or K, Q, Q over R squared divided by this particular charge, I can say that electric field is also K, Q over R squared. So the electric field has two definitions. One is force divided by charge, or simply due to a point charge, KQ over R squared. That's the definition of a potential field. Now, we also did a lot of art when it came to electric fields. And by art, I mean we drew vectors in the direction that electric fields would be at different points. And you should be aware of how to do that as well. The next situation is electric potential. Electric potential comes from electric potential energy in the same way that electric fields come from electric force. If I have a single positive charge here, and I take another positive charge, and I push on it, so I push it in closer, so that it's now here, and this new position has greater potential energy. I've done work on it. That work has not gone to kinetic energy, so it goes exactly to potential energy. In this case, moving it closer, I've increased the potential energy of this charge. The potential energy due to a single point charge is defined like so. KQQ over R. Notice this is actually what we get if we multiply the force times the distance moved. We define in electricity not just the potential energy, but also the potential energy that would be there if there were a positive charge there. So if, for example, I had a small positive test charge right here, it would have a potential energy of this, the potential, that would have a potential of the potential energy divided by Q, or KQ over R, where this is the Q that I'm measuring from. This V equals KQ over R is a measure of the potential due to a single point charge. With potential, we also talked about the potential lines, the equipotential lines. And if I were to draw an equipotential line around this positive, I draw a ring like this. This represents all the points near this positive where the voltage is the same. So I could say, for example, this is all 9 volts. Further away, less potential energy, this might be all 8 volts. Further away, this might be all 7 volts. Now, if I were to compare this to the field lines are always actually exactly at right angles to the equipotential lines, wherever they may be. So you should know how to draw the field lines, know how to draw the equipotential lines, and know how to calculate the values for both near a point charge. One special situation that we went over is the case where we had two plates, each of which had a distribution of charge on it. So let's say I have these two plates and I have positive charge up here and negative charge down here. What happens in this special situation is that in between the plates I get an electric field that's very, very uniform, meaning I would have the same force up at the top as I do at the bottom. So if this electric field here were 10 newtons per coulomb, this one down here would also be 10 newtons per coulomb. In addition, because I have such an even electrical field here, if I were to draw the equipotential lines are straight and actually evenly spaced in between these two plates. Now, once we got out here to the edge, they fringe off and do crazy things, and we'll just ignore that part.